morning. Today we will begin with the methods of estimation. As I mentioned early on, we will look at primarily 4 methods, I would say 4 classes of methods, 4 different philosophies for estimation: method of moments and the least squares approach, the maximum likelihood approach, which we have discussed mostly, and then the Bayesian approach to estimation. Before we begin, I just wanted to make a couple of points with regards to what we have discussed until yesterday, hypothesis testing. As I said yesterday, among the 3 approaches to hypothesis testing, my favorite one is the confidence interval approach, and the reason is very simple. Suppose I have to redo this hypothesis test for a different postulated value. So, yesterday the value that we had postulated was 90 degrees Celsius. Suppose I were to ask if 91, if I were to postulate the average to be 91, would such a hypothesis be rejected? And if you were to use a critical value approach or even the p value approach, you have to recalculate the observed statistic and then of course compare it to the critical value or your alpha. Whereas with the confidence interval approach, the beautiful thing is the confidence interval is for the truth, right, and of course the confidence interval will only change if the data changes, right, because the confidence interval has been calculated from your sample mean and sigma and root n. If any of this changes, the confidence interval will change, but if the postulated, it has got nothing to do with the postulated truth, and therefore even as I change my postulate, my confidence interval remains fixed and I keep comparing, I keep checking if the postulated value is falling within the interval. So, if I were to ask if 91 is a postulated value, you can straight away look at the confidence interval and say, well, that hypothesis also has to be rejected, and so on. Now, having said that, a word of caution is the confidence interval is not an interval of possible truths. That is one of the misinterpretations that people generally tend to make. It is not an interval of plausible truths. It is just an interval in which the truth is, we do not know where the truth is, and sometimes people would believe that the truth is at one of the extremes. No, we do not even know where the truth is. The truth could be midway in the interval or maybe at one of the extremes, close to one of the extremes, and so on. So, therefore, the confidence interval should be just taken as an interval in which the truth falls, but when it comes to hypothesis and when it comes to hypothesis testing, it is a very useful approach. Therefore, I would strongly recommend using the confidence interval approach. Of course, the choice is yours. So, I just wanted to make this point, and the other point is you can conduct all these hypothesis tests and construct confidence intervals and so on using R. The relevant commands are given in the video lectures. For example, t dot test would conduct a test for you for hypothesis concerning means. Then you have var dot test and so on. All those routines are mentioned in the video lectures. When I upload the slides, I will have a summary of the routines in R. Of course, when we talk about, when I show you how to estimate parameters using least squares in R, then I will also show you perhaps how to compute the confidence intervals using some built-in commands. Okay. So, with this few words, let me actually now get going with the method of different methods of estimation, and we will begin with the method of moments. The method of moments is something that we have seen before, right. I have explained the principle before. The idea is very straightforward. You write down the theoretical relations between the moments of the PDF, joint PDF, and the parameters that you are estimating. So, the parameter estimation problem is straightforward. We have already stated the problem of parameter estimation. So, there are some parameters that have to be estimated. We write down the relationship between the moments of the PDF and the parameters, and then assume that the estimates also satisfy these relations, which is a big assumption, right. They do not have to, because the estimates are always in error. What we begin with is the relationship between the true moments and the parameters. Now, obviously, this means that right from step 1, the method of moments assumes that the data that has been given to you is coming from a random process. When we move on to least squares, we will say that we do not have to assume randomness in the data at all, whereas method of moments right from step 1 assumes that the data comes out of a random process, pretty much like the likelihood approach. All right. So, to give you the math behind it, essentially what you do is you have mi, which is ith moment of the PDF, and you have g of theta, which is some function of the parameters. So, you necessarily do not get a form like this when I say that you have to strike a relation between the parameters and the moments. What you are essentially doing is there is a moment of the PDF, ith moment or nth moment, and you are striking a relationship between these two quantities. Sometimes this g of theta may be theta itself. As a simple example, suppose I am looking at estimation of mean, I am given some series, a standard problem that we have been discussing. The relevant moment would be the first moment x times f of x dx. Suppose I am, or let me use y here, y times f of I dy is the first moment. We know that is nothing but mu. Since mu is unknown, we would generally prefer to write mu on the left hand side. Okay. Now, this is a theoretical relation between the first moment and the parameter of interest. All right. Now, this parameter of interest is mu. In some PDFs, the parameter of interest may be something else, which need not be mu. So, you will have to rewrite this in terms of mu. Suppose I am estimating mean of a uniform distribution, right. So, what are the parameters of interest in A and B, the intervals. So, I would have to rewrite this equation here in terms of A and B. So, I would say A plus B by 2 is integral y f of y dy. Obviously, this single equation alone is not enough to get me the estimates of A and B. I would need to invoke a second equation. And what would be the second equation? There should be no hesitation if you have an answer. What would be the second equation in terms of moments? Second moment, right. You can pick any moment. You can pick any moment. It does not have to be the second moment, but the natural choice would be the second moment. And what would be on the left hand side? B square minus by 12. But we are not yet ready to use these equations until we replace them, these right hand side, with the sample versions, right. What do we mean by sample versions? You would replace this, for example, on the right hand side, you would replace this with the sample mean. That is, rather than saying sample mean, you would replace them, for example, with this, the first equation. That is the sample average. So, you are going to replace ensemble averages with sample averages, very simple. This is an ensemble average, right, across the possibilities, and here you have the sample time average. So, replace ensemble average is the time averages. That is the basic idea. Step 1, write the theoretical relations. Step 2, replace the theoretical expected averages or ensemble averages with the time averages. So, when you do that, you will get two equations and you can solve for A and B. When it comes to Gaussian parameters, straight away you get the estimate to be 1 over n sigma yk, which is nothing but y bar. So, first identify the parameters of interest, write the theoretical relations. If you are estimating parameters of a Gaussian PDF, the parameters are mu and sigma, and then you write the theoretical relations. These equations, these moment expressions do not change with the PDF, they are just integral y f of y dy. And of course, what I have not mentioned here is that you are looking at a joint PDF, but I have just suppressed that notation. So, straight away you get mu, whereas here you have to solve them simultaneously to get your A and B. Any questions on this approach? Very straightforward. So, this is the example that we just discussed, estimation of mean by method of moments. And if you want to estimate mean and variance, for example, of a Gaussian PDF, then you would require to write two equations. The first equation, both equations we have written on the board. The only difference between what we have written on the board and this example is the parameters are different. The parameters of interest are mu and sigma, whereas for the uniform PDF the parameters are A and B. Any questions? It is a very straightforward idea, there is nothing complicated here. However, the problem is with the uniqueness. I can use any moment equation, there is no restriction. I just need as many relations as the number of parameters. So, I could write, in this case we have used first and second moment, I can relate mu and sigma through maybe fourth moment of a Gaussian PDF. If I am looking at a Gaussian PDF, I can express the fourth moment in terms of mu and sigma, there is a relation. I could use that relation instead of the second moment. Do you think that will give you a different estimate? Yes or no? So, in general the problem with method of moments is lack of uniqueness, okay, and depending on which moments you have used, the estimates can change, and as a result of which their properties can also change, the bias, variance and so on. So, for example, here if you are looking at Gaussian PDF, already this mu is going to be estimated by sample mean. This sample mean is a beautiful thing. We have already shown sample mean is an estimator in the least square sense, in the MLE sense, now also in the method of moment sense, right. The only problem with this method of moments of course is uniqueness, but the other problem is I do not know in what sense it is optimal, right. At least with least squares and MLE, I know that I am solving an optimization problem explicitly, whereas here with the method of moments, I am not solving an optimization problem explicitly. I am not trying to minimize some sum square errors or maximize likelihood or even maximizing efficiency, nothing. I am just putting up a bunch of equations and solving, and the answer turns out to be sample mean. And if you are also looking at estimation of variance, what is the expression that you would get for, so mu hat would be this, and sigma square we have written the theoretical relation. If you were to use that theoretical relation that you see on the screen, what would be the estimate of sigma hat, sigma square? Sorry? Expected, no, so you, y minus y bar, by what factor? That is all, n minus 1. Do you want to work it out? You have to solve two equations. One equation is already telling you what is mu hat, right. You have to plug in the value of the expression for mu hat into the second equation. So, the equation that you have to solve is sigma square plus mu square. Well, now you are going to replace with the estimates, because you are going to use time averages on the right hand side, and here right. What is the time average of integral y square f of y dy? 1 over n sigma y square. What we mean by time average is whatever I am averaging in the ensemble, what am I averaging? Y square. Remember, f of y integral y square f of y dy, what is it? It is an average of y square, but in the outcome space, that is what we call as ensemble average. So, instead of looking at this ensemble direction, we are looking at the sample or the time direction. So, here is your ensemble or realization. The theoretical relation looks at this direction here, whereas what we use in practice is the time direction. There are green chalks here, I do not know how green would look on a green board, I will try it out someday. So, what we are looking at here is in the time direction, because this is all we have, all right. So, I have here this equation, I already have mu hat with me. So, what is the expression for sigma square hat? None by n? Put together. You should expect to see something of the form sigma yk minus y bar square what about the factor in front of the summation? 1 by n minus 1. You will get 1 by n minus 1. N minus 1 where do you get from? You will get 1 by n, right. So, the factor is 1 over n. What kind of an estimator is this? In what sense is it optimal? Where did we get this kind of an estimate? MLE, from the maximum likelihood approach we got this estimate, correct. So, the method of moment seems to be giving an MLE type of estimate, which means we already know this is a biased estimate. So, which also tells us method of moments can give you biased estimates, but we know it is asymptotically unbiased as well. So, what we learn is that the method of moments forces the time averages to satisfy the theoretical averages, which itself may seem in error, but by some magic it is giving you optimal estimates, right. Although we are not solving an optimization problem exactly, we are ending up with optimal estimates. In fact, it is true in general, you can show that the method of moments is optimal in some sense, although you are not solving, you are not formulating an optimization problem. But the problem with method of moments is lack of uniqueness. I may use a bunch of relations and some other person can use another bunch of relations. So, there is this choice that prevails and one has to figure out what choice of moments you have to use. Of course, people have studied and there are some standard approaches. The when it comes to applying this method to estimating parameters of time series models, so slowly we are talking about that. We have already seen that. Where have we seen the method of moments being applied in estimating time series models? Sorry? Yes. The Euler-Walker equation. You first derive the relations for the between the autocovariance of the process and the model parameters, and we have already spoken about it. Those relations can be used for two different purposes. One is, given the model parameters, I can compute the theoretical autocovariances, which is what ARMA or ACF does, and the other way around, given the ACFs I can calculate the model parameters. How do I do that? I use a method of moments idea. I assume that those theoretical relations that we have derived are also satisfied by the estimates of ACF. So, essentially I am going to replace the theoretical averages. ACFs are also theoretical averages only. Any theoretical property is an average, it is an average across the ensemble, because there is an expectation. Those theoretical averages are replaced by the estimates, and that is it, you get your Euler-Walker equations. So, the application of method of moments to time series models is very straightforward, but the question is how good these estimates, those estimates are, right. We have also shown, we also seen, for example, how to use this method of moments idea to estimate parameters of an MA1 model, and we found there are two solutions and so on. Now, it turns out that when you apply the method of moments to estimating autoregressive model parameters, you get very good estimates, very good in the sense you get efficient estimates. You get the most you get the same efficiency as you get with least squares and MLE. All right, but when you use the same idea to estimating parameters of an MA model, and I will talk about it, I will list all of these points later on, but I am just giving you some preview. When I use an MA method for estimating parameters of a moving average model, then I run into efficiency issues. I get estimates with high error. So, normally what is done is this Euler-Walker's method when it comes to estimating moving average model parameters, normally we use MLE, but MLE results in a nonlinear optimization problem. After all, you are going to maximize log likelihood, and that is going to result in a nonlinear optimization problem. Since nonlinear optimization problems require initial guesses, we use the Euler-Walker's method to kickstart the MLE algorithm. There are other ways to kickstart MLE algorithm, this is one of the ways, all right. So, you have to remember that not every estimation method is suited for all kinds of estimation problems. Okay. MLE has a more universal appeal to it, but method of moments does not. Now, having said that, somewhere in 1980s, this method of moments has a long history, but in somewhere in 1980s, an econometrist by name Hansen, he proposed what are known as generalized method of moments. In fact, he went on to actually become the Nobel Prize winner for his pioneering work in econometrics. A lot of methods that we learn in time series analysis come from econometrics, interestingly, and rightfully so, because in econometrics you have all kinds of complexities that you can't see in engineering processes and so on. Maybe biological processes are the ones that can beat the econometrics in terms of complexities, because econometrics involves first of all so many factors that cannot be measured and that are too complicated, particularly because there is a human factor involved in it. A lot of the effects that you see, or the observations or variables that you are seeing in econometrics, are driven by human decisions, and humans are very weird people. I mean, they are very difficult to model. Particularly their psychology is very difficult to model. So, you will see all kinds of complexities, and then you combine the psychological factors of many human beings, it becomes even more complex. That is why whenever you have a complex process that you do not know how to model, you turn to econometrics and there will be a solution. Whether it is heteroscedasticity or whether it is fractional integrating effect, whatever it is, any kind, or co-integration and so on, you do not hear this kind of fractional integration or co-integration and so on in engineering systems, but you will see that very often in econometrics. So, obviously people have spent a lot of time in econometrics, and this particular gentleman came up with this method of generalized method of moments. The basic idea in generalized method of moments is twofold. One, he said in method of moments you are writing exact number of relations as a number of parameters, and then you are forcing the time averages to satisfy those relations. Obviously, we know there is going to be an error. I mean, even if I look at this, what I am saying here is the mu is going to be satisfying this, and then saying that I am going to replace this ensemble average with time average, and then call that as an estimate. Obviously, there is an error, huge error. So, he says when there is error, it does not make sense to have exactly that many relations as a number of parameters. Write more relations. Write more relations. When you write more relations, you have a set of overdetermined equations. And generally, how do you solve overdetermined equations? Using a least squares approach, right. So, that is the key change that generalized method of moments brings with it, and that change is just amazing. You write more number of relations because you have now error in every equation. What basically he pointed out was that this relation cannot be satisfied exactly. When you know that certain relations cannot be satisfied exactly, have more number of relations written up, and then solve a bunch of overdetermined equations, typically using least squares or your favorite method, whatever method you have for solving overdetermined equations. It turns out that it has much better properties when it comes to estimation. In fact, he went on to show that it has asymptotically the same property as MLE. So, a generalized method of moments, which we are not going to discuss, but I gave you a brief idea. Some write up is given in my textbook, but you can go to the literature and read up more on generalized method of moments. There are packages that do that for you, but it is a beautiful idea. The only problem there again is how many relations should I write, and how does the estimate improve with the number of relations and so on. Obviously, there has been a lot of study done on that. So, turn to the literature to see what answers you have there. Okay. So, any questions on the method of moments? You should remember, method of moments does not set up an explicit optimization problem. The vanilla method sets up exactly the number of as many relations as many as the number of parameters, and then the choice of these equations that you are writing are not unique, but at least for some basic problems you can show that they result in optimal estimates. Sometimes they can give you efficient estimates depending on which parameters you are estimating, what estimation problem you are solving. Okay, so then we move on.